Hey, my dear students, exam time is here. I know you're all working so hard. So let's make sure we've absolutely nailed one of the most important chapters, the structure of the atom. We're going to break it down, make it super simple, super clear, and so easy to remember. Ready? Let's begin. Just take a look around you, your book, your phone, even the air you're breathing right now. Have you ever wondered what it's all really made of? I mean, if we could zoom in, and I mean really zoom in, way past what we can see, smaller and smaller and smaller, we'd finally get to the basic building block of everything. And that, my friends, is the atom. All right, so here's our plan for today. It's simple. First, we'll look inside the atom. Then, we'll check out Thomson's model, followed by Rutherford's big surprise and Bohr's solution. After that, we'll understand what gives an atom its identity card. And finally, we'll meet some atomic twins called isotopes and isobars. It's going to be a breeze. Let's go. Okay, so first things first. Inside the atom. Before we can even think about building an atom, we have to meet its family, right? The three tiny little particles that make up the whole thing. So this family has three members. In the center, in the nucleus, you have the heavy ones. First is the proton. P for positive, that's its charge. Easy to remember, nah? Then you have the neutron. And for neutral, it has no charge. And then, zooming around the outside, is the super tiny, super light electron, which has a negative charge. That's it. Proton, neutron, electron. The whole atom is just made of these three. All right, so now that we know about these three particles, the big question was, how are they all arranged? The first scientist to give it a guess was J.J. Thomson, and his idea, it was actually based on a fruit. Yeah, you heard me right. Thomson said an atom is like a watermelon. You know the red part of the watermelon? He said that's a big ball of positive charge. And the seeds stuck inside, those are the negative electrons. The most important thing he said was that the total positive charge and the total negative charge are equal. That's why the atom is electrically neutral. A pretty good first guess, right? But there was a problem. You see, in science, we are always testing things, and new experiments started showing results that just didn't match this watermelon idea. So this simple model, it was about to be proven wrong in a big, big way. And this brings us to our next hero, Ernest Rutherford, and his golden surprise. He came up with an experiment that completely changed everything everyone thought they knew about the atom. Seriously, this experiment is super famous. So here's what Rutherford did. He took a super thin sheet of gold foil. Imagine a piece of paper, but thousands of times thinner. And he shot tiny, fast, positive particles, alpha particles, at it. He thought they would all just go straight through, like a bullet through paper. But what happened next was totally unexpected. Most of them did go straight through, but some of them got deflected to the side, and a few, can you believe it, a few bounced right back. Rutherford himself couldn't believe it. He said, and I quote, "It was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you. Just imagine that, a huge cannonball bouncing off a tiny piece of paper." This one result completely proved Thomson's watermelon model was wrong. Something very tiny, very dense, and very positive had to be sitting in the middle of the atom. So based on this, Rutherford gave us a new model. He said, listen, the atom is mostly empty space. All the positive charge and almost all the mass is packed into a tiny little center called the nucleus. And the electrons, they're just revolving around it. But wait, this created a new problem, a big one. According to physics, a revolving electron should lose energy and, whoosh, spiral down and crash into the nucleus. But atoms don't collapse. So what was wrong? Rutherford's model was amazing, but it had this one big flaw. It needed a fix, and the person who came up with the solution was the brilliant Niels Bohr. Bohr's idea was so simple and beautiful. He said electrons can't just revolve anywhere they want. They have special, fixed orbits, like lanes on a running track. He called them energy levels or shells. And here's the magic part. As long as an electron is in its own special lane, it does not lose any energy. And that's why atoms are stable. These shells have simple names. Starting from the center, we call them K, L, M, N, and so on. Okay, now pay very close attention. This is super, super important for your exams. The rules for filling these shells. There are just 3 simple rules. First, the maximum number of electrons a shell can hold is given by a simple formula, 2n squared. Second, the outermost shell wants to have 8 electrons to be stable and happy. This is the famous octet rule. And third, you always fill the shells from the inside out. First K gets filled, then L, then M. Simple as that.
All right, so now we know the structure. But what makes a carbon atom different from an oxygen atom? It's like every atom has its own Aadhaar card, its own identity. Let's look at the numbers that define it.
The most important number on this ID card is the atomic number, which we call Z. It's just the number of protons in the nucleus. That's it. This number is the identity of the element. 6 protons, it's always carbon. 8 protons, it's always oxygen. Change the proton number, and you've changed the element itself. It's like a unique fingerprint. Next up is the mass number, or A. Now remember, electrons are super light, almost no mass, so the whole weight of the atom comes from the nucleus. So the mass number is just the total number of protons plus the number of neutrons. It tells you how heavy the atom is. And finally, we have valency. This is all about how friendly an atom is, how it combines with other atoms. Remember the octet rule, that atoms want 8 electrons in their outer shell? Well, valency is just the number of electrons an atom will gain, lose, or share to get those 8 electrons and become stable. It's basically its combining capacity. Okay, we're at the last topic, and it's a very interesting one. We're going to meet some atomic twins. Not exactly twins, but you'll see what I mean. First, let's talk about isotopes. Okay, think of the element carbon. Every single carbon atom in the universe has 6 protons. That's fixed. But some carbon atoms have 6 neutrons, so their mass number is 12, and some have 8 neutrons, so their mass number is 14. See, they are both carbon because they both have 6 protons, but they have different numbers of neutrons, so they have different masses. These are called isotopes. And you know what? These isotopes are incredibly useful. An isotope of uranium is used as fuel in nuclear reactors. An isotope of cobalt is used in cancer treatment. And an isotope of iodine is used to treat goiter. So you see, they are very, very important in the real world. Now, the other type of twin is an isobar. Isobars are kind of the opposite of isotopes. Here we have atoms of different elements, so they have different numbers of protons, but they have the same mass number. For example, argon has 18 protons and calcium has 20 protons, but they can both have a mass number of 40. So different elements, but same total weight. And that's it. That is the entire story of the atom. From the tiny particles inside to the brilliant scientists who figured it all out. We've covered the whole chapter. You guys did a fantastic job. Just remember these main points, and you will do great in your exams. You've got this. But wait, before you go, I want to leave you with one final question to think about. We just learned that an atom is 99.9% empty space. So why does your chair feel solid? Why can't you just push your hand right through the wall? It's a fantastic question, isn't it? Something to think about. Okay, all the very best for your exams. I know you are going to be brilliant.